Hello everyone and welcome to this webinar. My name is Michael Evangelista and I will be your moderator for today. Just a few reminders that you are in listen-only mode to avoid unnecessary background noise. However, you can type in your questions anytime you want in the chat box and those questions will be answered by our panelists in a Q&A segment. By the way, the recording and certificate of this webinar will be sent out in 2 days' time. And our topic for today is about the high voltage GIS circuit breaker testing. It will be presented by our expert from Sweden, Mr. Nils Wacklen. So without any further ado, let's start the webinar. Nils, go ahead.
Thank you, Michael. My name is Nils Wacklen, and good afternoon to all of you listening to this webinar. Welcome. And I'm product manager for the circuit breaker testing equipment in the Megger factory located in Sweden. And I have been working with the circuit breaker testing equipment for, what is it now, 36 years, I think. So that's me, and then I will just jump right into the presentation. I will turn off my camera. So high voltage GIS circuit breaker testing. Yeah, GIS stands for gas insulated switchgear. So we have all the acronyms clear. So and the agenda for today, or the outline, I will first speak a little bit about challenges in GIS testing, and then something about contact resistance measurement, and at last the contact timing measurement, and then contact resistance measurement. So first, just let's take a look at an air insulated breaker and a gas insulated switchgear. Yeah, it looks pretty different, and there are different challenges for the two types. In the left one, the air insulated breaker, it's easy to have access to your measurement points of the circuit breaker, access points for both timing and for resistance measurement. However, there are other challenges you have to climb. There are overhead lines which are energized and so on. In the GIS, here on the right side, there are other challenges. You barely see where the circuit breaker is located, because everything is sealed, everything is encapsulated in the housing, and everything is grounded, so it's a safe environment in that sense. But the problem is where to find the access points to test timing and contact resistance. So this is a typical one-line diagram for a substation, GIS substation. So if we look at, you have your bus bars up here, 2 bus bars, and you have disconnector switches, and this is a combined disconnector switch and earth switch. And you have your power circuit breaker here, current transformer, voltage transformer, another earth switch down here. And we will have a look at this one a little bit closer. You see that this one on the diagram, it's marked in this way, and this means that it's an insulated earthing switch. And we will talk about this a little bit more later on. But anyway, this is a crucial thing when you test in GIS. So the access points usually for GIS timing and contact resistance is to find one of these insulated earth switches. The arrow here, and for timing you can actually do the measurements from only this point. For contact resistance, you need also a second point to attach your test leads. And another example is in older installations, there might not be any of the insulated earthing switches. The substations that doesn't have those ones installed. So in that case, you have to find other access points. So in this example, you go outside the substation, outdoor, to the transformer, and on the transformer bushing, where you have access to the primary circuit, you can access your test leads. And in that case, normally you set you install a temporary working ground at the transformer, because you have to this earthing switch need to be open in that case. So you have to put an extra temporary working ground here to be on the safe side. And the next slide I will show is similar to this one. The one line diagram is very similar, but instead of the transformer, there is a line. So I will show a picture of this. So this is, the red building is the substation, and you see the bushings here that goes to a line, an outgoing line from the substation. So in this case, there were no insulated earth switches inside the substation. So we had to put a temporary working ground on the outside, and then you can put your test leads between this one that belongs to the primary circuit and to ground. This point is grounded, so you have your test leads here. So for the timing, so that's absolutely possible to do like that if there is no other solution. So there are some prerequisites for timing of GIS circuit breakers with both sides grounded. So that there must be access points for the test leads, of course, and the two I mentioned are the insulated earth switch, and which is also actually required for conventional timing as well, which I will show later on also. Or you can use other access points, for example, bushings to the transformer or to a line. It's possible. It must be possible to fit ferrites around those earthing shunts / jumpers / links. There are several names of these connections between the housing and the insulated earthing switch. So and the rule of thumb is that if the breaker can be timed conventionally with single ground, it can most probably be timed also with dual ground. So and another thing that is important to consider is that all parallel ground paths connected to the insulated part of the earthing switch, for example, shielded cables, maneuver shafts for the operating mechanism, those must be isolated high frequency wise by means of ferrites. So now a little bit about the principle of an insulated earthing switch. So in this case, you see this earthing link is removed. Normally it's placed here, and normally then the whole housing of the GIS station is grounded. You see here is one ground, the housing is grounded. But when you remove this switch, the link, this part will be isolated from ground. And you see that this earthing switch inside is connected to this part, to the insulated part, which means that when you remove this link, one side of the circuit breaker becomes floating. So, so it's separated from ground, and the circuit breaker will be grounded only in one side. And this means, of course, that conventional timing is possible. And the access points for your conventional timing would be one point here, and your measurement loop would be this, and through circuit breaker, and through the next to the second earthing switch to ground, and back again to your instrument. So that's a test loop for a single ground timing test. And if we look at the insulated earthing switch in the safety perspective instead, you actually want to keep this link placed there where it should be, because as long as the detachable shunt is in place, the housing of the insulated earth switch is grounded and safe, and you have a safe working zone. So, however, when you remove, once the shunt is removed and the circuit breaker is in open position, the housing of the insulated earthing switch ends up in a floating state, exposed to capacitive coupling from nearby line parts. See, all this part becomes actually dangerous, because here on the left side you have the bus bars and only this connector switch in between, and in the GIS it's very short distances, and that's also why the amount of capacitively coupled currents are normally at higher levels compared to in the air insulated circuit breakers. So yeah, you have to be very careful when doing this. So it's an unwanted situation. So some arguments to test with dual ground. So that's of course to apply to standards. The IEC standard states that all parts in a substation must be grounded during test, and so on. And you can also save time by not removing links, where it requires less workforce in some cases. In some organization, you have a dedicated person that is authorized to remove ground, and this person doesn't need to be there because you don't need to remove the ground, and so on. And of course, it's less intervention in the GIS, thanks to that you don't need to remove the jumpers, and also sometimes you have maneuver shafts or the shielded cables that go to the insulated part, and those ones do not need to be removed either when testing with dual ground method. And when you remove something, you also have to remember to put it back again, and perhaps you have to use the right torque to tighten the bolts and all that stuff. So and clean before and so on. So it's more work than you think to remove things. As I said before, the capacitively coupled currents tend to reach higher values in GIS due to the small distance between the live parts and the isolated parts. And also one hazard is that the GIS environment, it kind of gives you a false sense of security, because everything is normally connected to Earth. Whereas in the air insulated circuit breakers, you can see your overhead lines, and you can hear the noise from the corona effect and so. So it is more obvious that you're exposed to danger when you're in an air insulated station. So everything is for your own safety. And very quickly, the hazards with a single grounded system, that's accidental re-energization of installation, not very likely, but lightning strike could be one danger. Capacity coupled, maybe the biggest danger, or the most probable danger. And if you're unlucky, you could be electrocuted, and if you're lucky but unlucky anyway, you can get burns from the arcing, or secondary injury by tumbling from ladder due to electrical shock. So all these things you need to avoid, you want to avoid. So now I will explain how the DCM technology and the earth jumpers, how it works, that you don't need to remove them and so on. So you'll find this link or jumper to the earth insulated earthing switch, and you put the ferrite on that, and you hook up your timing cables from the DCM box on each side of the ferrite. This is the easiest way to hook up. So you have your DCM. DCM stands for dynamic capacitance measurement. And the secret of this technology, in the simplified explanation, is that we use a high frequency alternating current, AC, and it's in the megahertz range. And this is injected in the circuit breaker loop. So if we walk through the test path here, we go from this way and here down, and here through one earthing switch, through the circuit breaker, and through the second earthing switch to ground, and then return back in the housing of the GIS and back to your test equipment. And why doesn't the current go in the link? Yeah, that's because the ferrite blocks high frequency. That's a simplified explanation of this method. And if you have maneuver shafts, they can actually remain, but you have to put ferrites on them. And it can also happen that you have if you have an independent pole operated circuit breaker, there are maneuver shafts between phases because you have one operating mechanism for the earthing switches, but yeah, so you have maneuver shafts between the phases to operate the earthing switches, and those ones also need to have ferrites attached. So ferrites need to be attached to maneuver shafts that go between phases. And sometimes you have a cable for the supply of the motor, for the spring charge, and so on. And that is usually, or it's always, have a shield, a grounded screen or shield, and that one needs to be also isolated with the ferrite. Oh, sorry, like that. So, and some small traps that you can jump into when doing this kind of measurements is that, yeah, here we have the housing of the breaker and this insulating material, and in the lower part you have your insulated earthing switch, and here it's the link or the jumper or shunt, and you have a bolt that fixes this link to the housing to get connection between housing, link, and link in housing. However, this bolt need to be isolated with the insulation washer, and I will show you the reason why. And this is normal. It normally is insulated like that, but sometimes if the breaker has been tested in a conventional way, where you remove this link every time, this washer might not have been mounted again. So it's missing. So then I will show the difference between when you have the washer, and in this case there is no washer, and what happens then. Yeah, in this case your current is forced to go through this link. That's the only connection is through the link. But if you have no washer, there is a parallel path through the bolt. And in this situation, your ferrite that was shown here around the link, ferrite doesn't have any effect because this part that goes through the bolt is not blocked. So in this case, it's important to look for the insulation washer. So everything is insulated. Okay, so some advantages with the DCM technology. DCM technology is the dual ground timing measurement, just to be clear. It catches the closing and opening of arcing contact according to the IEC and IEEE standards. This is important that it's the arcing contact operation, not the main contact. This is what the standard says. As opposed to if you would measure in this way with a DRM method, then you would probably only sense the operation or detect the operation of the main contact, because the parallel ground is very, very low in the GIS installation. So it's very, very hard to catch the arcing contact in that way. But the DCM technology does that. And this is the only method detecting contact bounces in GIS breakers with both sides grounded. So it can actually sense if there is contact bounces at the closing, for instance. And it can handle more than one parallel ground path, provided that you can isolate them with the ferrites. And it's a lightweight solution due that it's a very low test current. And another advantage is that there is no risk of tripping protection relays, thanks to that you do not inject high DC current with high rate of change through the current transformers. So that can be a risk otherwise. And you don't need to demagnetize the current transformers because it's a low AC test current. So now on to some case studies this is a GIS transformer breaker with insulated earthing switch. We have up here is the insulated earthing switch, and the transformer here. It's a star connection, a star configuration, grounded in the middle point, in the midpoint, and there is no disconnector between the transformer and the circuit breaker. You see there is no disconnector switch. So another way to see the same thing is this. So your bus bar, disconnector, power circuit breaker, two earthing switches. One of them is insulated, and there is no sectionalizer or disconnector switch here between circuit breaker and the transformer, which is outdoor, of course, the transformer. So in this case, even if there was an insulated earthing switch here, it was actually impossible to test this breaker in the conventional way also, because there was no disconnector. So and the star configuration of the transformer, which means that the windings were grounded in the midpoint, and also between between the phases, you only have the resistance of one winding between. So this means that in this sense, with the conventional timing, all three phases were actually connected in parallel on one side, and also on the other side, because the other side is grounded. So there was no way to test this breaker, not with the conventional method. So no way, no with big intervention, of course. So what they have to do to test this, they have to remove this flexible connection to the transformer that was outdoor, from the bushing to the transformer. And then you could also remove the earth link on the isolated ground switch, and then you have your access point for a conventional timing at these points. So that was one way, but it's a lot of work to remove this kind of flexible connection. So with the dual ground, the DCM timing, what we did was actually to keep this connection, flexible connection. Just put the ferrite around the earthing link on the isolated earth switch, and then you have your access points on each side of the ferrite. And then, yeah, it was possible to time this breaker. So, and actually it was looking like this. It's a Siemens 8DN9. So you have bus bars here, these connector switches and earthing switches, circuit breaker down here, and here also the earthing switches, and up on the top you have the insulated earthing switch. In a close-up picture, you see here a ferrite also mounted around the link. And you see on the other side of the circuit breaker there were cable bushings immediately, so no access point here. Actually, the same example, but in this case there was no earthing switch here inside. So it's a similar example. This was actually the one I showed in the beginning of the presentation also. And yeah, in this case you have a transformer outdoor, and quite a long distance, like 25 meters in between. So in this case, you have a temporary working ground on the outside. So because you need to have this, okay, I think next slide. This internal ground switch need to be open in order to get your test loop for the conventional timing. So then this is open, and the switch here need to be closed, of course, in order to get your loop, this connector switch, and you have to remove the flexible connection to the transformer. So then you get your access point from the bushing here through the disconnector switch, through the circuit breaker, through the earth switch, and the return back in earth going to the test instrument. That was the way they tested. But with the dual ground method, you can actually keep this temporary grounding. You can then it's the same configuration of for the rest of the switches. This must be closed, this must be open, this must be closed. But you can keep the flexible connection, and your access point will be on the bushing and on the ground. Your test loop will be actually the same as for conventional timing through the circuit breaker through the earth switch and back in the ground. The difference here is that you have your parallel ground here, but that parallel ground is big enough to not, or the impedance created by this parallel ground is big enough to not disturb the measurement. So it's also possible, if needed, you can put a ferrite on this parallel ground, the temporary working ground. Next is another example, actually in the same substation and older type of GIS installation where there were no insulated earth switches. So, and in this case, there was not even a disconnector. It was just a long line to the next substation that was like 20 kilometers away. We take this picture instead. So yeah, okay, it was turned around. Here you have the substation, the indoor part to the right. You have a circuit breaker, and this grounding here was not possible to remove. That was the one closest to the bus bar. And in this case, since it was a parallel line in service, there is quite a lot of induced current due to long parallel lines. So you have a lot of induced current and also capacitive coupled currents, of course. So in this case, they needed to put the temporary working ground on the line, and then disconnect this flexible link to the bushing, and then they can measure with conventional timing your access points and the test loop just in this ungrounded part through the circuit breaker and back through ground to your test instrument. So in this case, we could keep this flexible connection and keep flexible connection, keep the temporary grounding, and you just put the access point for the DCM leads on the bushing, between the bushing and ground. So you have your test loop, the same test loop, but you have this parallel ground here, but that doesn't affect your measurement due to the higher impedance in this cable. So you have very much advantages with testing in this way. So now I will quickly show some examples of earthing switches. They can look very, very different. So this is an ABB breaker. So you have in the middle point, you have the earthing, and the links go out to your three phases like a star connection. To the right is also an ABB kind of link. Here it's another type where you have like a bar going all the way, and this bar has connection to all three phases. So in this way you have to put ferrites between the phases also to isolate them from each other and from ground. Here another type of earthing switch, or the isolated part, and yeah, so there are many different configurations. This one I think it's a GE breaker, where you have in this part is what you see here is the earthing link, and this is also a GE breaker where you have actually 6 earthing links in this way. This is a French breaker, the MG, with the link. This is pretty common look of the earthing link, and this is the right side, you have, I think it's a Siemens breaker. This is definitely a Siemens breaker, where you have the same design here as seen before with a bar between the faces, and you have two earth connections like that. This is also Siemens with, yeah, you see here, the link is here. We can put the ferrite in that position. And we also have snap-on ferrites that you can put on cable links like that. So, and we provide a ferrite kit for this kind of measurements. Okay, now jump into contact resistance measurement on GIS. So we have seen this picture before. So now you know everything about the insulated earthing switch and so on. So now just jump into it. So contact resistance measurement. So then you need some kind of micrometer, and you connect it. And this time it's better to connect in each side of the circuit breaker like that. So in one side at the earthing, at the insulated earthing switch, and the other side at the other earthing switch. So, and what happens when you start to inject current here? Yeah, the current starts to go this way through the circuit breaker and back to your instrument. But you will also have a part going through the link and through the housing of the circuit breaker. And actually, this is not a small part, it's a bigger part than the part going through the primary circuits. So I will show that shortly how it works. And then of course you have also your voltage sensing leads like that. And now, and one example, the values can differ of course, but this is taken from reality, from a Siemens breaker, the DN9 actually, where the resistance in the circuit breaker loop, which actually is two earthing switches, one here, plus the resistance in the circuit breaker. The whole loop here had the resistance of about 150 microns. And the earth loop, that is actually the housing of the GIS, plus the earthing link, this part had the resistance of 75 microns, about half of the value of the resistance of the circuit breaker loop. So then if you apply the rules for calculating two resistors in parallel, then the resulting resistance will be 50 microohms in this case. So actually your micrometer in this case will show 50 microohms. And that's not the truth, of course. So let's have a look at the equivalent circuit. In this case, you have your circuit breaker loop with 75, your earth loop 75 microohms, and your circuit breaker loop 150 microohms. And you inject current. Let's say you inject current that is 3I, and then the current is divided. So in this part, through the circuit breaker, only 1/3 of the current is going, and 2/3 is going through the earth. So it's just a Kirchhoff's law. You have the current division, three times the current here, and so on. You understand. So this is important actually when you test according to the standards also. So in order to get 100 amps measurement current through the circuit breaker, you need actually to inject 300 amps, because 200 amps is going through ground and only 100 amp will go through the breaker in that case. Just an example. And it can be worse. I have seen cases where you actually have to get 100 amps through the circuit breaker. I think it was over 500 amps you had to generate from your micrometer in order to obtain 100 amps in the circuit breaker loop. So that's a good thing to consider if you want to test with the standards, with the current stated by the standards. So yes, so you have your micrometer again, and yeah, as I said, or I didn't say it, but to obtain a proper resistance of the circuit breaker loop, the current going through earth must be compensated for. So you must deduct the earth current from the generated current to know the current going through the CB, circuit breaker. And that is done by means of the current clamp. You just connect it to your earthing link here. And then the resistance can be calculated as the voltage drop divided by the current going through the circuit breaker loop, the true current through the circuit breaker. And this will result in the correct result of your circuit breaker loop, in this case 150 microohms. And this also works if you have parallel earth links. In this case, where we have a second link here, you can just put a second current clamp, and they need to be connected in series. So you get a summary of the currents going through earth links. So this is just an example how to connect the clamp-on CTs on the earth link. So now I think it's the last slide. Just so the summary of dual ground contact resistance measurement on gas insulated switchgear. This is the only safe method for accurate contact measurement on GIS. And the CB circuit breaker remains grounded on both sides. While in the conventional method, you can remove the link, but that gives a hazard. And dual ground method, you can measure current through earth link by means of current clamp. And this is especially crucial to compensate for the ground current in GIS because of the extremely low earth loop resistance. So you will get very corrupt values if you don't compensate for the earth current. So again, the resistance of the circuit breaker loop is the voltage drop divided by the generated current minus the ground current or the earth loop current. And also remember that you have to minimum generate 3 times higher current in order to obtain 3 times the wanted measurement current you have to generate. And in this case, on GIS, it's also important, since you are injecting through CT, that you use the ramp up, ramp down function to avoid tripping of protection relays. And the CTs should be demagnetized after test. So that was my last slide, and so I hand over to Michael. Thank you.
Yes, sir. Yep. Thank you so much, sir, for that wonderful presentation. So guys, let's now move on to the question and answer portion. But before doing so, please be reminded that there will be a pop-up message or survey form on your screen when you close this webinar. So please don't forget to answer that one, because that will really help us a lot in improving our webinars. So, Niels, we have some questions here, and let me read it for you. First question here is for GIS testing on 1.5 system, please update the precaution. Does the DCRM test contain the resistance of all the conductor between the injection leads?
Sorry, your sound disappeared. Can you post the? Can I see the question somewhere?
Hello, yes. Can you hear me again?
Yeah, but it comes and goes. Yeah.
All right. So when you open the questions box, you can also see the questions there.
Questions bar. Okay. Where can I find it?
Okay, so let
Is
me.
it the chat, or no? Not the chat.
No, not the chat, but it's the other tab. Says it has a level of questions. So the first question is for GIS testing on 1.5 system. Please update the precaution. Does the DCRM test contain the resistance of all the conductor between the injection leads? So what are the precautions when doing the DCRM test?
DCRM. Okay, but the DCRM test is that was not the subject for this webinar, actually, but I can, because the D, I suppose, means dynamic contact resistance measurement.
Correct.
Yeah, and the thing is that for GIS, there is only one way to do dynamic contact resistance measurement on a GIS breaker, and that is to make it with single ground. For dual ground, it's not working fine because of the relation between the ground loop, the very low ohmic ground loop, and the more the arcing contact, which is first, it is unknown, but it can be up to in the milliohm range. So you have a milliohm resistance in parallel with something that is micro. So that is very hard to detect the arcing contact, and that's what actually you want to do with a DCRM test. So my recommendation is, even though you're exposed to more danger, but if you want to do the DCRM, it should be done with single ground.
Okay, so yep. So maybe we can make another webinar just regarding to that DCRM. Right?
Yeah.
So yeah, watch out for it, guys. We will do another webinar for that. Well, another question here. When we test the GIS circuit breaker contact resistance, then disconnector resistance and CT primary winding resistance are added. Is that the right approach?
I need to yeah, of course. I mean, there is no other way because the only access point you have, the access points are the switches. So in GIS, there is no other way to test only the resistance of the power circuit breaker. So you have to do the yeah, how to say, if you have something, if you have a good reference value for that loop, you can see the differences if the resistance go up, for instance. But in that case, you can never know which one of the devices that that is causing the increase of resistance. So that's a problem because you have 3 or 4, including the CT primary, of course, in series, and that's life. So you cannot insert a probe only measuring the voltage drop across the power circuit breaker. That's impossible unless they design the circuit breaker in that way, of course. Then it could be done, but I have not seen such breaker with bushings for test bushings in that sense, only for sensing voltage drop across power circuit breaker. I don't think that exists.
Yeah. So meaning to say, Niels, you are just going to compare phase per phase the resistance value, and that will be the way for you to assess the resistance, right?
Yeah.
All right. Okay. And also they can do the trending or historical data to compare the previous test result of that.
Yes, of course.
All right, so another question here. How much variation in result is permissible in field tests, in factory tests in case of CRM?
Actually, I don't know.
The
That is
variation?
something. Yeah, that is something that you have to ask the manufacturer because it can be different. I'm not sure if the standard says something about that.
Yeah, I guess I remember that one.
Do you
Well,
think so?
anyway, yeah, I remember that one that there is a standard mentioning the yeah, it's the NETA standards.
Okay.
So when you compare the three phases, so the difference should not exceed 50%.
Okay.
Yeah.
Yeah, thank you.
So that's all the questions that we have for today. So guys, if you have any more questions, you can also send us an email and we'll also try to answer back through email. So I guess that concludes our webinar for today. And at this point in time, I would like to say thank you everyone for joining us, and also thank you so much, Niels, for your time here in Asia. Hope to see you again in the other webinar topic.
Yeah,
And yes,
thank you for attending.
Yeah, we will be sending you the recording and the we will try to send the PowerPoint as well if Niels permit to, if the management permit for us to send it. But we will be definitely we'll be sending you the recording of this webinar, including the certificate. But yeah, in 2 days' time. Right. So again, thank you everyone for joining us today. Please have a good
Thank
day and
you.
stay safe. Thank you so much, Neil. Have a good day.
Thank you. Thank you. Bye bye.
Bye bye.